As we transition into looking at electric current and electric circuits, I'd like us to think for a minute about this kid's toy right here. In a minute, you'll see me turn this on, and this little stair stepper thingy will be pushing the monsters up the steps. They'll then head on back down. So the first thing I would like you to observe is, are there any monsters getting used up here? Apparently, upon looking at this, we see that we don't use any monsters up. We also don't create any new monsters. We just seem to keep pushing the same monsters through over and over. And it turns out that this toy is an exact gravitational analog to an electric circuit. The stair stepper thingy is moving the monsters from where they gravitationally want to be up to where they gravitationally do not want to be. And it's having to do non-conservative mechanical work on the monsters against the gravitational force that's pointing down. So we have a gravitational field pointing down, the monsters feel a gravitational force pointing down, and the stair stepper thingy has to do mechanical work to lift the monsters up. Then once the monsters get onto the track, they are going from where they gravitationally don't want to be back to where they gravitationally want to be. And you'll also notice there's a fair amount of friction here, and we'll see that there are friction-like elements in electric circuits as well. So in a regular battery in an electric circuit, it's the same deal. We are moving electric charges from where they electrically want to be to where they electrically don't want to be. And then the electric field will shove the charges around in the rest of the circuit that's not the battery until they return back to where they electrically want to be. So as I run this again, the next question I want you to ask yourself is this an equilibrium state? And if we take a look at this after all, we see that we're constantly pushing monsters through. Doesn't really seem like anything's changing. So is this an equilibrium state of this system? Turns out no, this would be the equilibrium state of the system with all the monsters sitting down where they gravitationally want to be. But it looked like the system was basically staying steady, so what is that? This turns out to be an example of what's called a steady state system, which is a state of disequilibrium that is being continually maintained at a certain level by some external agent. So let's start looking at steady state systems by looking at an example you've probably seen before. You may remember seeing a diagram looking something like this when you were learning about weather systems and the water cycle. So at least the way I was taught it, as clouds develop when we're going over a mountain or whatever, it will cause rain to happen. Now, gravity is going to pull the raindrops down. are going to go down the river and eventually down into the lake and the ocean and whatever. Now, in equilibrium, the water would all just end up here. All in the lake, probably frozen too. But what we have is the sun heating the water. This causes evaporation. So the thermal energy being provided by the sun is what is providing an energetic input to allow us to lift the water molecules from where they gravitationally want to be back up to where they gravitationally don't want to be. So we then form another cloud. And also the sun will drive the winds, and then eventually the cloud runs over another hill, and we start raining again, and it loops around and around and around, just like our monsters. Here, the sun is playing the role of the stair-stepper thingy. Its continuous input of thermal energy is what is lifting the water molecules up from their gravitational happy place up to some place where they gravitationally really don't want to be. So we've increased the gravitational potential energy of the water molecules. And then we go over here, eventually fall back down, decreasing, decreasing, and back along. Viscous drag along the way takes energy back out of the system, causing some heating to the surface of the Earth. So what is keeping this process going? Pause for a moment and then get back with me. So yeah, it's the continuous input of energy from the sun. If we were to suddenly magically turn the sun's rays off, then eventually all the water would drain its way out and it would find its way down into this lake. So we say that steady state, which is what we call this kind of a system, is a situation of disequilibrium that is externally maintained at some level. So in the case of the stair-stepper thingy, there was actually a chemical battery that was providing the energy necessary to turn the little motor to go and lift the monsters up against gravity. And then gravity pulled them back down. Here, the sun heats the water and lifting the water, and then the water goes back down. And this process will continue only for so long as the sun continues to burn. Of course, we've got over 5 billion years before we have to worry about the sun turning into a red giant and expanding to a point where it's the size of the Earth's orbit and we all get consumed, and then we don't worry about the water cycle anymore. But I digress. So with that, let's go and think about doing this with a Van de Graaff generator. Because remember, a Van de Graaff generator is a form of a form of a battery. So remember, with a Van de Graaff generator, and we literally have a conveyor belt that is spinning around. I will make the conveyor belt spin this way so that we can, let's just say I've got some plate here or something. I got it going this way so we can take electrons off of this plate. And we will physically move the electrons to the left. And then we will drop them off here. and eventually put them onto this plate like so. So in the process, what's happening to the charge that's on this plate over here? Yeah, it's becoming positive. In this plate over here, yep, negative. So if I just continue letting this process run as is, will I be able to run it forever, assuming that I keep putting work in on the conveyor belt? No. And the reason for that is because as we remove electrons here, making this plate negative, putting electrons onto here, making this plate positive, making this plate positive, making this plate negative, we start to build inside our Van de Graaff battery an electric field pointing to the left. I will call this E interior. And our electrons here will feel an electric force from this interior electric field in which direction? Pause and get back with me. Yeah, it'll feel a force to the right because remember F equals Q times E. So since E points to the left and the electron charge is negative, that means that the electric force that the electron feels is to the right, which makes sense. This is electrically where the electrons want to be. This is their happy place. And this is where they electrically don't want to be. So we posited that, for lack of a better term, we'll just call it friction, that the Van de Graaff generator is literally mechanically dragging the, electrons along on the conveyor belt doing work against the electric force. Well, it can only provide so much force. At some point, the electric field gets too big and it just literally can't move the charges anymore. So if we wanted to keep this process going, how could we do that? Well, one way we could do that is we could hook up some sort of a load. It could be just as simple as a short circuit, which you should never do in practice. So we're going to imagine that this is some resistive wire, and this is purely for safety reasons. Because if you use normal low resistance wire and directly connect to both ends of the battery, what can happen is things can get real hot real fast, and no joke, you can actually start a fire doing this. So this is very much a do not try this at home kind of thing. So I'm going to label this as high resistance wire. Safety first. And just to give you some idea of how short circuits are no joke, we'll be getting this more later. But as a cautionary tale, once as a broke student, I was replacing my own car battery. And this was before they were doing the things where they're putting protective covers over the terminals. And as I was removing the connections to the battery, it was really cold out. I lost my grip on the wrench, and the wrench managed to just accidentally fall onto both terminals of the car battery. The terminals of a car battery are usually lead, and this was one of those crescent wrenches or adjustable wrenches, and it had a big hole on one end so that you could hang it up on a pegboard. The ridge, the top part of that hole, happened to land perfectly in the middle of one of the terminals of the car battery. So much current flowed so fast that the lead heated up to the point that it was actually melting. And my wrench sunk about halfway down the post before I was able to grab some sort of insulating material to force the wrench off of the battery. So nowadays, in order to make sure that literally that can't happen, car manufacturers have little flexible plastic covers that go over the terminals, literally to protect against accidentally dropping a wrench on the terminals, like happened to me. So that's probably not a likely thing to happen in the future to people, but there are many themes and variations on this. It's also for those same kind of reasons. If you are ever jumping a car or getting your own car jumped, it is very important to follow those step-by-step instructions that they give in the vehicle manufacturer's manual. It's again designed to protect against just such kinds of things happening. If that short circuit had run for much longer, there's a very serious risk of actually boiling the chemicals inside the battery and having a potential explosion of the battery with acid flying all over the place. It would not have been a good thing. So if you're going to try to do this at home, do not use wire. In fact, just don't do this. Let's think of this as a thought experiment. So with all of those caveats in mind, here I'm even going to say, don't build this. So with all those caveats in mind, let's think about what would happen to the fringe field. Because remember, since these are not infinite plates here in my thought experiment, this means we must have a fringe field. So again, what will happen is our fringe field will look kind of dipole-ish, and it turns out that it'll bend around to match the shape of the wire exactly in this case. Oops, sorry, I got my arrowheads pointed the wrong way. There we go. And there will be other fringe field lines as well, like for instance these, etc. I'm not going to draw them all, but the important point is that there is a fringe electric field. And so within our high resistance wire, what's going to happen with our electrons? Well, it's going to see an electric field that is pointing to the right. So which way is an electron right on this plate going to feel a force? Pause and get back with me. Yeah, it's going to feel a force to the left. And so our electron will now, once we are outside the battery, it'll be feeling an electric force directed along the wire. Now, how exactly charges get around corners, give me a video or so give me a few videos to get to that. It'll turn out that there will be surface charge distributions built up and stuff like that. But there is an electric force acting on this. And also, there is some sort of an analog to kinetic friction. I'll put that in quotation marks there, just like I do here. There's some sort of an analog to kinetic friction because, like I said, this is high resistance wire. The electrons, it turns out, will have collisions with the partially shielded nuclei in the wire, imparting kinetic energy and losing kinetic energy in the collisions as a consequence. So what will happen is the charges will move around the wire at basically constant velocity. So here we'd have our electric force, and here we'd have our analog to friction here. And just the electrons will go around counterclockwise, both inside and outside the battery. So we got that the electron current is flowing counterclockwise everywhere, both inside and outside our Van de Graaff generator battery. So which way is the conventional current flowing? Pause and get back with me. Yeah, because the conventional current goes against the direction of negative charge flow. We will be saying that we have a conventional current that is flowing clockwise, both through the battery and through the wire. Okay, so with that, let's go and visit this a little more with a chemical battery and see how that might vary a bit. So we will again go back and imagine our galvanic cell. And again, because I'm not a chemist, I'm giving you one of the world's worst battery chemistries here. Again, I don't want anything exploding. Don't actually build any of this. So we'll imagine having a zinc rod sitting inside of zinc sulfate and a copper rod sitting inside of copper sulfate. So for chemical reasons, the zincs on this rod here, or we can imagine it to be a plate. Sure, let's make it a plate. The zincs on this plate here would dearly love to go into solution. So the chemical reaction, so they will dissolve for a bit, and we'll be putting zinc ions into solution, which will be making this terminal negative. We then go ahead and look at the copper side here, and again, it's the same deal. Like we were saying before, the copper ions will generally want to come out of solution and plate onto this electrode here. And so here I took positive ions off, leaving behind negative charges. Here I'm putting positive ions on, building up positive charge. All right, so if I just let these sit here, will these reactions continue to run forever? Pause and get back with me. No, of course not, right? Because what starts happening here is the zinc solution becomes positively charged, right? And so the zinc ions are going to, at some point, are going to say, hey, despite the fact that the chemical reactions would love to do work to take me off of this electrode and put me into the solution where I'd be chemically happier, electrically speaking, it just can't do enough work to pull me off, so I'm going to remain on the plate. And in fact, we are going to be building an internal electric field here. So again, we will go ahead and just following the same kind of notation we had before, I will label this as E interior. Our electric field will point right to left because it goes from the positive terminal to the negative. And so looking at a zinc, for instance, we can look at the forces on the zinc, and we can see that there's going to be a huge electric force now pointing to the left on my zinc. There were other forces that were due to the chemical reactions, so I'll just call it F chem. I really don't want to get into the mechanism behind all of that, but it has to do with trading off valence electrons and stuff like that. I was trying to pull it to the right, but again, it can only do so much work to pull it off. Again, same kind of picture over here. The electric force is going to point on our copper ion is going to point to the left. Well, we can make this go a little longer if we can at least reduce the charge that's being held in the in the solution by inserting a salt bridge. So we will go ahead and stick in our salt bridge. So sticking in our salt bridge, let's make it potassium chloride in water solution. So what's going to happen here? Well, as I pull coppers out of solution, I'm leaving behind negatively charged fluid here. So this is going to attract in potassiums. And here, this is going to attract in chlorines, because the zinc sulfate solution is becoming positively charged. So now will it run forever? No, it just gets to the point where we're totally limited by the electric field between the plates. So how do I get this to run, keep running? Well, I get this to keep running by attaching some leads to this. And this time, instead of thinking about a high resistance wire or something like that, I'm going to stick a toaster here, which is actually just a whole collection of high resistance wire. But again, it'll be the same deal. The fringe field will follow a dipole kind of shape here. So going out there, coming in here, and then here, like I say, when there's a wire in the vicinity, or a toaster for that matter, it will follow the shape of the wire. Like so. We'll get into how that happens a little bit later. But again, it's the same deal. Now, let's think about the electrons that are sitting right in the immediate vicinity here, like say just even on this plate, right? The electrons are, whoops, I've got my arrowheads running the wrong way again. Sorry about that. There we go. Let's get the electric, whoops, and make them red. There we go. So make the electric field vector, there we go, run like that. So now we've got an electric field, the fringe field, let's label that, is pointing to the right just immediately off of this plate here. So if I'm an electron sitting around the surface of the plate, which way am I going to feel an electric force? Yeah, to the left. Because again, negative charge times right is left. So feel an electric force, and once again, just like before, because of the resistance within the wire and the toaster, there will be an electrical equivalent of kinetic friction. So it'll move at a constant speed all the way through here. I mean, we can repeat this over here, say like at this point right here. The electric field is pointing that way, so the electric force would point to this way, and again, there would be some sort of analog to kinetic friction here. Again, just because of the electrons colliding with partially shielded nuclei in the wires. And we wind up having on the outside an electron current that is flowing counterclockwise. But let's take a look carefully at what's happening in the fluid, or in the battery. In the battery, we have chlorines that are moving to the left. So there we have a negative ion current that's flowing right to left. And then let's pick a slightly different greenish shade here. Our positive ions, the zincs, the potassiums, and the coppers, are all moving left to right. So let's think about the conventional current everywhere. Which way is the conventional current going outside the wire? Yeah, outside the wire, it's going around clockwise because it'll go against the electron current. What about inside the battery? Well, it both goes with the positive ion current, so left to right, check, and against the negative ion current. The negative ions are going right to left. So here the electrons are going, the conventional current for the associated with the negative ion current is still also going left to right. So all of our current in the battery is going left to right. So that's just, again, more clockwise. So both inside the battery and outside the battery, our conventional current is flowing clockwise. Alrighty, so in the next video, we'll be taking a look at resistance and seeing how the electric potential being applied across a resistive device relates to the current that can possibly go through it. Catch you over there.